welcome to the SAMPE Technical Committee webinars. My name is Tanaya Mandel, and I'm the chair of the High Temperature Materials Committee, which is now Extreme Materials. And we will be having Dr. Stephen Nutt talking today. So, yes. So our technical committees right now are advanced manufacturing, bonding and joining, materials for extreme environments, sustainability, and thermoplastics. And then you can log on to SAMPE 365 under groups and search for the TC that you want to join, and then you can join us. So we also have our State of the Technology Industry report. You can also download our last year's copy from the SAMPE online store in the link below. We're also doing one this year. So please join us. Our member experience, you have so many benefits. You can be having the journal subscription, a digital library, meeting discounts, event discounts, excuse me, meeting seminars and literature, many networking opportunities, leadership opportunities, and there's also a career center. So please join us. Our next conference is in Long Beach in May, and it's returning to Long Beach. I haven't been to this one, but I did go to the one last year, and I would like for all of you guys to join us, and it'd be great to see our PC in person.
Yeah, and I think Chris Locke's going to say a couple words about our upcoming conference.
Absolutely. Thank you so much. Great intro. Hi, everyone. I'm Chris Locke, Director of Marketing and Membership Services here at SAMPE North America. I'm based out of our Diamond Bar, California offices, and I do truly want to invite you to join us at the Long Beach Convention Center on May 20th through the 22nd. Long Beach is kind of home for us. This is exactly the birthplace of aerospace, and what happened in aerospace really had its roots start here in California. And so coming back, I think the last time we were in Long Beach was like in 2019, no, before then, maybe 2018, before my time. And so it's exciting to be coming back there, and it's a really robust show. We've got a lot of great workshops. We've got a co-partnership that we're doing with the U.S. Department of Energy that will be about hydrogen, which is going to be fabulous. And then, of course, we have a lot of papers, presentations, and other tours going on. We've got just a plethora of opportunity for you to join us there. This is our premier advanced materials and process engineering conference and exhibition in North America. So it's really important that you join us here and just get a taste for all of the great conference programming that's going on. We have a wonderful keynote speaker who is the Stephen Hines, our Vice President of R&I for Science Co. So he's going to be talking about the work he does for his composite materials division. We have some really great tutorials going on and some panels as well. And speaking of which, today's guest speaker, Dr. Stephen Nutt, is actually going to be presenting in Long Beach, and he's going to be talking about evaluating process routes for producing ceramic composites. So I do invite you to listen in today on today's webinar, but then register in Long Beach to hear Steve in person. So with that, I'll turn it back over.
Thank you. I would like to let everyone know this is being recorded. So we were going to post this in about 2 to 4 weeks. It will get posted on our SAMPE 365 landing platform, and then it'll shortly go into our YouTube channel. So we should have this available in a couple weeks. Also, we'll do a Q&A at the end. If you could, please put your questions in the Q&A section instead of the chat section up at top. And you can put those on throughout the meeting, and we will address those at the end of the meeting. We want to leave it, maybe 10 minutes to go through those. So I'll let Tanaya take it on from here.
Thanks, Chris. So this is our high temperature materials leadership, or as now it's the extreme materials. I am the current chair. I'm Tara Mandel. I'm a PhD student, but now I'm a PhD candidate, actually, in material science and engineering at A&M. Our vice chair is William Guzman. He is an R&D materials development engineer at Renegade Materials Corporation. And Chris, who just is, all of us are on the call, by the way. And Chris is a process development scientist at ACCI Specialty Materials. And our newest addition is our co-secretary, which is Jaden Pollock, who's a graduate student at University of Nebraska-Lincoln. All right. Please join SAMPy 365 and get involved. And there's a link right there. So upcoming high temperature material webinars, we have Dr. Calvin Stewart from Ohio State University on April 11th, 2024 at 4 p.m. Eastern. And the title is Materials at Extremes.
Appropriate.
Yes. So I would like to introduce our speaker is Dr. Stephen Nutt. He's from the University of Southern California. He is a PhD in material science from the University of Virginia. He's affiliated with as a fellow of American Ceramic Society. He's the Vice Dean of Research at USC, he's a department chair at USC, and also the director for Center for Nano-Imaging at USC. And with that,
Okay,
we want you to start.
Yeah, I'll turn my screen off and Steve, go ahead and start sharing yours.
Well, thank you for the introduction. And I understand that the High Temperature Committee is now the Materials for Extreme Environments Committee. Okay, that was a last minute edit. Thank you. I'm going to be just talking about different process routes for ceramic matrix composites. I think for a lot of people, they're not aware of the choices. A lot of people are much more familiar with the choices for processing polymer composites. You know, the vacuum infusion, RTM, pultrusion, et cetera, et cetera. But for ceramic composites, it's a different story. All right, so let's get started. Okay. Yes, what are they good for? This is a chart from Jim Steibel at GE that I lifted. I think he's okay with it, but it just is a bubble chart essentially showing the relative specific strengths as a function of service temperature for different classes, different families of materials, you know, the well-known, you know, metal alloys and occupy the sort of the left lower quadrant. Polymer composites for specific strength on the upper left region, but ceramic composites on the lower right. And so high temperatures for one. That's one of the main motivators for considering ceramic composites. Now, the specific strength looks, you know, not too impressive relative to other material families, but that can be sort of extended upwards at those service temperatures with protection layers, which I'll talk about downstream in this presentation. All right. I remember many years ago, I worked with a fellow at what was then the United Technologies Research Center in Connecticut. His name was John Brennan. He's one of the early sort of pioneers in ceramic composites. And I still remember, because he said it several times, with ceramic composites, the name of the game is fracture toughness. Ceramics are brittle. Everybody knows that. So they're never going to be used in many applications unless that limitation is addressed. Now, yes, they're inert. They retain, you know, properties to high temperatures, but brittleness and environmental resistance, brittleness, this is a weakness, and environmental resistance is a plus. If one can impart fracture toughness, boost it even just a little, then that's a real game changer. There are various approaches to boosting fracture toughness with ceramic composites. Surprisingly, porosity is actually an approach, and I'll talk about that downstream as well. But the most well-traveled approach and is what we call weak interfaces. Tuning the fiber matrix interface so that it is strong enough to transfer load, but weak enough to debond and deflect cracks. And then also surface treatments can help boost both toughness and environmental resistance. I'll talk about applications. One of the best known applications are nozzles for gas turbine engines. The white component there is a ceramic composite. And boy, like gangbusters, the funding spigot has been turned on for hypersonic applications because, well, yeah, I think you all know the reason for that. These are vehicles that are going to require high temperature composites, including ceramic matrix composites. There's almost no other way around it. And we'll talk about more of those applications next. Well, we talk just about applications. Everything sounds, wonderful, but we have to also be honest and talk about the challenges, and the problems. All right, the three main sectors I'm going to talk about are turbine engines, space applications, think rockets and rocket components, and hypersonics. Another sort of comparison chart showing much the same thing, only this on the vertical axis is material surface temperature. And then on the horizontal axis is the approximate time of use, meaning like when these materials were introduced and became commonplace in applications. If you're not familiar with some of those application acronyms there, IMC is intermetallic compounds, TBC is thermal barrier coating, FGM, functionally gradient materials. I think everything else people can figure out themselves. All right, so you can see why there's interest in CMCs because they're in the upper right of that little chart. This is a well-traveled image. I've used it many times myself. It's just a jaw-dropping example of a ceramic composite being used for in the tail section of a turbine engine produced by GE. This is the GE. I'm not sure if it's the Passport or the LEAP engine, but it's called an exhaust gas mixer. And you can see the geometric complexity of that part. It mixes bypass air with exhaust air. That's why it's called an exhaust gas mixer. That's a aluminum oxide composite. Aluminum oxide fibers, aluminum oxide matrix. Produced here in Southern California, by the way. Composites Horizons makes that. Yeah, we'll talk about how the process by which they make it as well. That's kind of interesting. There's been attempts to go farther than just the tail section of the engine and introduce ceramic composites into turbine blades. That is a bit of a challenge because of the toughness requirement. But this is from GE, and the yellow blades there are the ceramic composites, and they're yellow because of a coating on top of them. More common in GE engines are other parts. This is the LEAP engine and a part called a shroud. Okay, so these engines are extremely complicated, but basically this is there are a bunch of these shrouds that go and encircle the hot zone. This is another part called a combustor liner. So the name suggests, and the position in the engine suggests, these are in the hot zone of the engine. These are not in the warm or the cool zone. These are really in the hottest part. And GE has made hundreds of thousands of these parts, and they've flown their engines millions of miles. I say that because Jim Steibel said it. He gives a wonderful talk, by the way, and he's now retired, but he gave a nice overview talk of GE's use of ceramic composites. Turbine vanes. If you've ever seen one of these things, they're one of the most complicated little parts you'd ever hold in your hand. You can hold that part in your hand. It's about a few inches in dimension. You can see all the perforations, the compound curvature, the flanges. These are typically made, by nickel-based superalloys. Now, if we try and introduce ceramic composites, there's kind of a hybrid approach that's outlined here. This involves a ceramic composite plus metal component plus environmental barrier coating and thermal barrier coating with monolithic silicon nitride. Just about every class of material imaginable. This is an interesting little sentence that I lifted from the literature. And I thought it was interesting because, well, I assume they're still called United Technologies, although I know that Pratt Aerospace has been sold to Raytheon, and I'm not quite sure how that works out. Test high pressure turbine vanes, combination of these materials. And you can see this is a route that they are pursuing. This is fairly recent, this quote, in the last 5 years. And in aerospace, parlance, that's fairly recent. Yeah, so coolant is going to be involved, coatings will be involved, multiple materials will be involved. Okay, now that was turbine engines. Now we turn the page to space. And this is a little article lifted. You could probably recognize this. This is from Composites World. This is a so-called black rocket engine. And it's interesting because of the multitude of different materials used in the design. And they actually are using what is often considered a defect in composites as an asset, a feature, and that's porosity. So they're trying to make a microporous carbon-sick CMC for transpiration cooling. This is German work. And let me see if I can just switch here and get the audio from this. Okay, it's just about a minute, but it is kind of entertaining and gives me a chance to catch my breath. Passive cooling. Supply of coolant. CMC liner for transpiration cooling.
Dr. Nutt, we're not seeing anything.
Oh, I'm sorry. Let me try again then. Sorry about that. Seeing this now? Sorry, sharing.
Nope.
No,
not
we
yet.
still can't see anything. Yeah.
Okay. Start again. And this is the material that we're going to be talking about, the transpiration for transpiration cooling.
We're still not seeing anything yet.
Yeah, I don't know if you have to hit the share screen and then choose
The
the
green
actual.
button.
Yeah.
Wow. Okay. I'm just going to abandon that and go on then, because that's well, anyway, that was a really cool video, but I'll have to figure out some way to get that in next time. This is the carbon sick material, CMC material that they've designed and are using for what is called transpiration cooling.
Still not seeing anything.
Yeah, Dr. Nutt, you need to share your screen again. It unshared your
Okay.
screen. Yeah.
Sorry about that.
Yeah, that's fine. And we can get the link from you in the future for the video and potentially be able to share that with everyone.
Yes,
see that
would
now?
work.
Yeah,
Yes,
you're
we
good
see
now.
it.
This is
Okay.
good.
Sorry. All right, so this is where we were last time. And I'm going to be talking about this blue material in the graphic on the right. It's a microporous carbon sick used for transpiration cooling. And there's an actual image of the material. Next, I'm going to show, this is X-ray CT showing, this is really almost Swiss cheese. And it's that way by design to deliver the fluid, the coolant fluid, to the assembly, and so they've turned what is normally a defect into a feature, I guess. And here on the lower left shows just the interconnected pore network for this CMC material, and that is an unusual application. The first one I've seen where they're actually trying to use it to deliver a coolant. And of course, you know, this material also has to withstand substantial heat as well. Now, turning our attention to the last area of application, the hypersonic vehicles. So one of the engine types that's being considered for hypersonics is called a scramjet. And what I did there is put two graphics, one for a turbine engine, one for a scramjet engine, to show that there are parallels, even though they look very different, and they actually are quite different. But there are combustors, nozzles, and sort of a compressor or compression surface. It's difficult to get actual images of the actual engines of these vehicles, but there's a big effort to actually combine these two engines, because a lot of the vehicles will be much more versatile and useful if they can fly at different speeds, not just hypersonic speeds, and that requires multiple sort of modes of propulsion, and both of which will use ceramic composites. Okay, so this is a quote from David Glass of NASA, who's leading a long effort there. Moving beyond insulated aluminum airplanes to a vehicle with multiple thermal protection system and hot structure approaches. Okay, so now we have to sort of open the Pandora's box. It's not just CMCs, it's TPS and EBCs and other coolants and so forth that are going to have to be employed to make these vehicles fly. Now, I mentioned some of these acronyms, the EBCs, environmental barrier coatings, and TBCs, thermal barrier coatings. TPS is thermal protection system. All right, and this is a nice graphic showing like the 5 things that these coatings have to protect against, and it is a very tall order. See, chemical compatibility, CTE mismatch, dissimilar materials, phased stability at high temperatures, and for a lot of these materials in these systems, they're carbon-based and they produce silica, and the silica can volatilize, particularly in the presence of humidity. And in the center is something called CMAS, which most of you probably are familiar with. Basically, that's dirt. It stands for calcium magnesia aluminosilicates. The primary ingredients of airborne particulate, i.e. dirt. Well, that causes problems for ceramic composites. It ends up floating into the engine, where it ultimately melts and then becomes a dangerous reactant, essentially. You thought things were complicated, look at some of the schematics that are in the literature for approaches to dealing with these 5 challenges in the circle on the left. This is the structure of a coating to be put on top of a ceramic composite, silicon carbide composite, and it's presently in use. This silicon at the bottom is effectively just a bond layer. if you're like me, you probably, and this is the first time you've seen it, you probably can't even remember what YB stands for. That's a rare earth element, ytterbium. And the DS and MS are disilicate and monosilicate. Okay, so these are dual layer coatings on top of silicon with a thermally grown oxide on top of that. Holy cow. So, and then the danger here are the things floating around in the atmosphere, water and oxygen, and how they can react with these compounds. So there are even more elaborate approaches that involve not just the environmental barrier coating in A and B, but a thermal barrier coating on top of that. So that is to, as the box indicates there, that's a CMAS barrier. And then below that is volatilization protection, and below that oxidation protection. Okay, it's getting, this is state of technology today. That's a 2021 review article. Let's turn our attention to the last acronym, the TPS, the Thermal Protection System, which has been in use for a long time. Okay, everyone has seen these things. They're ablative shields. They're single-use protection, typically commonly used on re-entry vehicles, often phenolic-based composites that char, and the char protects sufficiently long, and then they have to be replaced. This is a TPS being made, produced before launch. You can get a sense of the scale there. There are other approaches, though, that have to be used for cooling and protection. The TPS on the left is semi-passive cooling. For hypersonic vehicles, they will require active cooling, meaning circulating a coolant. See the blue arrow in that diagram there. And the second, last one is the transpiration cooling that was used in the German rocket design, where you're basically flowing coolant through a component of the structure. Those are three different approaches to cooling materials and managing the heat. All right, how do we make these ceramic composite materials? There's about 5 different answers. The first one that's been around for quite a while is known by 2 acronyms. One is RMI for reactive melt infiltration. It's also known as LSI for liquid silicon infiltration. And you can see in this graphic here that basically starting with a carbon fiber polymer composite, and then pyrolizing that to create a sort of a porous material, and then basically infiltrating with molten silicon, not silicone, as that annotation mistakenly says there, to flow into, via capillary flow into the porous preform and react to form silicon carbide. The appeal, and that's a big one there, particularly low cost. Okay, the cost of these process routes is generally quite high. This is probably one of the lowest cost routes. And the problems or the challenges, the porosity is not very well controlled, nor is the composition, and particularly residual silicon. Okay, silicon is a sort of a low melting component in this assembly, and that's going to be a problem. It's difficult to get all of the silicon to react to silicon carbide. So the applications tend to be things like brake rotors for automotive. There's a company in Germany called Brembo that is owned by SGL, and they've been making these, and they're I was visiting there last summer. They're planning to double their production capability. They're selling them for sort of high-end passenger cars. They've been used for quite a while on race cars, but now they're entering the commercial market. For one, they don't produce any break dust when they wear. They last, multiple times longer than cast iron, and they're much lower density. Of course, they're higher cost, but anyway. And turbine engine parts are also made by this process route. A second process route is CVI, chemical vapor infiltration. The appeal is you make large pieces and very good control of the matrix composition, unlike reactive melt infiltration. Okay, this is basically chemical vapor deposition, but it's chemical vapor infiltration into a fiber preform. The challenge is, well, it's costly, it's very slow, and closed porosity. Porosity levels, as I understand it, between 5 and 10% are common, and cycle times are days, not hours, like 5 days, 10 days. PIP, polymer infiltration and pyrolysis. It's an iterative process. It's used for carbon-carbon composites, has been for a long time. And basically you start with ceramic particles and a fiber preform, blend these things, impregnate with polymer resin, and mixed with ceramic particles, and then you pyrolyze to produce a CMC. Again, because it's iterative, it's slow, and there's closed porosity, upwards of 5% typically. Oftentimes, the number of PIP cycles used is anywhere from 3 to 6, and each cycle can take over a day. Figure it out. This is the process route that's used for the exhaust gas mixer. And basically, it's a very simple one, and that's part of the appeal. We start with oxide prepregs. They're also produced here in Southern California by Axiom Advanced Materials. And Composites Horizons uses their prepregs to make the parts. It's basically just pressureless sintering in air. The appeal of an oxide fiber, an oxide system, is you don't have to worry about oxidation. You can see it goes through a lot of the same process steps that a polymer composite goes through, because you're making prepreg essentially, and laying up the prepreg, vacuum bagging it. Even, okay, we use the term cure. It's not really cure, but what comes out of the autoclave is a green state ceramic that can hold shape. And then it's subsequently sintered in a really big furnace. There's the problems. It's a non-uniform infiltration of the ceramic slurry and non-uniform porosity. Okay, talk about that in a minute. A fourth process route is just pressure-assisted sintering. There's two variants. One is very well known, and that's hot isostatic pressing. Okay. The second one is maybe less well known, field-assisted sintering, or commonly known as spark plasma sintering, where a electric field is applied during sintering, either DC or AC, and that greatly accelerates the densification process down to like minutes. Okay, so you can, that's a huge appeal right there. Okay. There, in any press operation, there's going to be size and shape limitations. This is a kind of an interesting variant that developed by a Japanese company called Nutt, NITE, for nano infiltration, nanoparticle infiltration and transient eutectic. I'm not going to try and explain all that, but basically it's infiltration of a slurry into fibers, just like the previous slide, but different constituents here, not ox. Now we're talking about silicon carbide nanopowders. And then layering up the plies, just like you would with prepreg, and pipping, hot pressing, to form either carbon-sic or sic plates. Pipping is a relatively slow process, but well established and widely used, versus the FAST or SPS process, you're talking about densification in a matter of minutes. And finally, I'll talk about analyzing CMC microstructures. Here's that well-traveled schematic that's showing the principle of fiber toughening by interface crack deflection. And so you can see, tuning the interface microstructure and properties to achieve this type of behavior is critical to imparting toughness. Here's an example of a crack in an oxide composite deflecting around fibers. And that's actually a good thing. You want that type of behavior. Porosity is, though, as it turns out, is a difficult thing to quantify. In terms of like a single number doesn't adequately characterize porosity. You can say, well, the porosity is X%. That doesn't begin to tell the full story because there are different types of porosity, different shapes of pores, different sizes, different locations, and it's a big undertaking, but yet it's important. Look at the Oxox composites. You see this, we're going to sort of, the end product is on the left. That's a ceramic composite. The matrix is either alumina or alumina plus silica commonly, powder, and then fibers made by 3M. Those are Nextel 610, 500 satin, 4500 denier, 13 micron diameter, and pores. So pores are part of the microstructure. Okay, now the pores have a wide range of sizes. Okay? And therein lies part of the challenge. Now, sample preparation, typically a 10-hour production cycle, temperatures of 1,000 to 1,200 degrees C. This is a series of micrographs showing increasing sintering time top to bottom, and left to right is increasing sintering temperatures. And you can see these are kind of difficult measurements to make because porosity is an elusive and multifaceted quantity. So it's a lot of scatter. Here, 8, 10, 12 hours at 3 different temperatures and not a whole lot of difference. And large error bars on all the measured values, but you can see porosity in each case is upwards of 20%. Okay, this is not polymer composites where you reject parts because of more than 1 or 2% porosity. This is what flies on engines with 20+% porosity. We can begin to understand sort of the three-dimensional nature of the pores by volumetric imaging, X-ray CT, and what you see on the left here is images of pores. Pore volume is color-coded, so yellow is larger volume than green, is larger volume than purple. And then on the bottom of is frequency on the vertical axis and a volume on the horizontal axis. And you can see that one pore might actually account for a fairly large fraction of the overall porosity if it's sufficiently large. This is a higher sintering temperature, same sintering time. You can see the pore sizes and pore shapes. They tend to be quite elongated along the fiber directions, which is not too surprising. These images here on the right show what porosity looks like in, this is the type of porosity that want to achieve by design. This is not a problem. This is actually what we call good porosity. And this is some statistical distribution of the pore diameters. These pores here tend to be relatively equiaxed. Okay. But this is a dilemma. This is an open question right now, and I don't think anyone yet has the answer. Because porosity is a feature of these types of composites. But it has aspects of not just how much volume, but the aspect ratio, the geometry, the distribution, the location, and it goes on and on. So just getting a handle on some of these questions requires a lot of work, and not just two-dimensional SEM imaging, but volumetric imaging. Thermography, although it has much less resolution than the other techniques, is useful for global sort of distribution of porosity. Now we're going to turn our attention, I need to get finished here pretty soon, to a much more common application. And this is ceramic brake rotors by field-assisted sintering. This is a work in progress. This is a very low magnification showing the distribution of there's matrix is basically silicon carbide and zirconium diboride. The fibers are carbon fibers. They're chopped in bundles, and all of this is sintered in a matter of minutes. I mean, this is not a really homogeneous distribution of phases. They're the carbon fibers. The big sort of islands are silicon carbide, and in between the islands are predominantly zirconium diboride. Little white flecks that you see there are not surface dirt. That's actually alumina yttria sintering additives. And this in greater magnification, you kind of see the sintering additives in white, the zirconium diboride in gray, and the darker region there is silicon carbide. The few little black islands are what remains of carbon fibers. You can see the map of carbon there, and you can correlate that with the image on the left. There's silicon carbide. This is just a composition maps and the zirconium diboride. Looking at the carbon fiber bundles, actually the fibers have sintered together. You can see they're no longer round, and in fact, they actually have some sort of faceted boundaries where they fused together. And then upper left, you can see that the fibers that are isolated by themselves have actually reacted with the matrix component. The bad actor here is zirconium diboride. It really attacks the carbon and reacts pretty strongly with it. That's not a showstopper necessarily for brake rotors. More composition maps. I call it in this slide segregation. I'm not quite sure where how to discriminate between segregation and inadequate mixing. We're trying to deal with that right now. I think I'm beginning to think it's just inadequate mixing of the powders to start with. Just more maps, zirconium, carbon, boron, oxygen, silicon. All right. One of the challenges with any composite is, like, how do you measure the uniformity of the phase distribution? You can look at it, and by eye, you say, well, that's more uniform than this other section on the left. But there are ways to quantify this, and it involves some tools, tiling or tessellation tools, where you subdivide the microstructure into small regions. And this is one type of tessellation called Voronoi tessellation. And that will enable us to actually measure how uniform the dispersion is in different iterations of the production. Yeah, controlling phase distribution is really important. That's something that vendors have to deal with. There are a lot of different ways to go with this, and different fiber forms to play with. And finally, I'm going to look at, we're going to talk about this nanopowder infiltration and transient eutectic approach, which is basically has been licensed by Axiom, and they're using it. But we're looking at the effects of temperature, sintering temperature, on the infiltration and distribution phases in the structures to try and guide the selection of process parameters. This is basically a big task. there's no manual to tell you what to do here. You've got to go through these steps. One of the things with these the so-called spark plasma sintering or field-assisted sintering is carbon fibers react, and they react quite a bit. And for load-carrying applications, this is going to be a problem. These fibers are uncoated. They will certainly require coatings to prevent this type of reaction. But even with reaction, cracks still find their ways around the fiber, so which is actually a good thing for ceramic composites. We've also looked at crack paths in this material. Basically, we're seeing interlaminar cracks, transverse cracks. You can see these things propagating through the layers. But the result of all of this sort of preliminary work has been to sort of identify a process temperature, sintering temperature that seems to work better than others. We're actually measuring the interface strength is a really important challenge, but a very difficult thing to do. One of the approaches that we've used is basically fiber push out. We basically used a focused ion beam to machine trenches underneath these little ledges here and machine a very smooth flat surface that we can use a flat bottomed indenter to push out individual fibers. We use the SEM imaging capabilities to position fibers directly under the indenter. When we measure load versus displacement, we can then use that as a tool to discriminate the effects of different fiber coatings, different process histories. I'm not going to say a lot about this. The coatings are a big part of this, and believe me, groups at Oak Ridge, at GE, and elsewhere have spent a lot of time on these coatings. It is an aspect of ceramic composites that it has been worked on extensively and will continue to be worked on for quite a while, because these coatings are a way to boost, the service temperature. Unfortunately, it's a real Pandora's box. Once you start applying coatings, coatings on top of coatings on top of coatings, and it's very, very complicated and costly, as you might imagine. Rare earth silicates are basically the compounds of choice right now, but you can see there are other components to the surface treatment there as well. All right, let's wrap up here. This is what the landscape looks like for applications in the next 5-10 years. Some of them are relatively mundane, I would say, or very common, the automotive applications. Others more exotic, rockets and hypersonic vehicles. New materials, refined process tools, and I think we're going to start to see the use of computational material science tools to try and identify compounds that will extend the service temperature and service life of these materials. Yeah, big thing is cost. These materials are quite expensive. Even for composites, they're very expensive. I'll wrap it up there. Thank you.
Thank you, Dr. Nutt. This was a very wonderful presentation. We do have some questions in the Q&A. Oh, you got an applause button. Look at that. All right. Our first question, sorry, that's very loud out here. First question we have is from Motoshi, and it is there any manufacturing method that is preferable for making smaller structures and any method for a larger structure?
Yeah. Personally, I think for cost, the reactive melt infiltration beats all the others at present. I think for small parts, field-assisted sintering is very fast and is compatible with small parts. Complexity of geometry, though, would mean that tooling would have to, match or provide the geometric complexity. I don't, the largest parts are probably on rockets and maybe some of the hypersonic vehicles, but I believe, there is no single, clear best choice there for larger parts. Obviously, you're not going to be able to make parts larger than a press if you're using a press. But I think, when you look at these things and try and compare them, that's useful, particularly if you apply one metric like cost, and then RMI stands out. In terms of speed, then field assisted sintering stands out. And yet, almost by far the greatest number of like carbon products are made by polymer infiltration and pyrolysis. Now, some of that may be inertia, like they've been doing it for 20 years. They're not going to change overnight. But I don't know. I don't think it's a really clear answer, but it may be that there isn't a clear answer, except for the aspect of cost. But anyway, next.
All right, our next question is, what is happening right now in terms of recycling or LCA analysis in the CMC?
Yeah. For recycling these materials, to my knowledge, nothing. For LCA analysis, if anyone's done any of that, I suspect it's NASA and General Electric, and I haven't seen any shared. For recycling, that for composites in general, it's a sorry state. There's almost no recycling of even polymer composites, which is a much smaller hill to climb, in my opinion, than ceramic composites. So we have a long ways to go there. A life cycle analysis, I think, is a really valuable and important tool to assess different routes, different approaches to recycling. But in terms of, carbon footprint and embodied energy, these materials, they stand out like a sore thumb. We desperately need, some solutions, to recycling, and not just downcycling, but true recycling. And anyway, that's a good question. Fortunately, I guess the volume of materials for ceramic composites right now is very small compared to polymer composites. Brake rotors, though, that could change things. And I think there are prospects, though, for brake rotors to do exactly what they've done with carbon brake rotors, and that is resurface them. You don't have to throw them away when they're worn out. You can, that's what's done with aircraft brakes right now. And so that could be a really good approach to returning worn components to service for at least brake rotors. But for the other things, I don't have any answers. Sorry. Next. Okay.
The next question is additive manufacturing a good option for CMC manufacturing?
Good question. We're collaborating with a group in Germany, and they've been working on this approach for quite a while. Basically using additive manufacturing to sort of lay down the ingredients of a composite that would subsequently be pyrolyzed and infiltrated with liquid silicon. So yeah, people are doing that, and that's an appealing route to make more complex geometries. Not just flat panels or mildly curved panels, but you can do some really intricate shapes with printing like that. But the group is at Bayreuth, which is in Bavaria, Germany, at the university there. And they have an entire almost an entire department working on ceramic composites, and 3D printing of the sort of the precursors is has been an active area of activity for them. So, yeah.
All right. And our last question is, what modeling methods are you familiar with to simulate the manufacturing process and predict porosity, cracking, and fiber reactions? And are there any commercially that are available?
Ooh. Yeah, wow, that's a sort of a big hole in my portfolio right now. I think there's two types of modeling that are really needed and valuable here. One is process modeling, and that's what I'm most interested in. And not much has been done. For one, the different process routes require quite different process models. And so I think you have to pick one route that you're going to try and simulate with your process model. For mechanical models, I think things are much further along. The mechanics people, I think, can handle, through finite element codes and so forth, can incorporate, the salient features of porosity, tailored interface strengths, and so forth. So I'm sure there are academic groups working on mechanics simulations of CMCs, but process modeling is an area that I'm really keenly interested in. And yeah, if you have any suggestions, please send them my way. All right, well, thank you for your attention, everyone. And if other questions arise, you know where to find me by email.
Thank you so much, Dr. Nutt. Does anybody have anything else to add also from the committee?
No, it was a great presentation. I like the images. Those SEM or TEM images were really high resolution.
Yeah, one comment about those, if anyone's ever spent any time on a polishing wheel with abrasives, that hard materials and hard porous materials are not particularly easy to prepare. We rely quite heavily on abrasiveless polishing with ion beams. It's called an ion polish. It's actually, I think, almost an essential tool to preserve the pore structure of these materials. So
you fib the surfaces on the parts you're imaging, focused ion beam.
Yeah, we'd not fib. No, fib way too slow. But there's a tool called broad beam ion polisher. There's half a dozen vendors that sell them, and they're really valuable for sort of prepping the surfaces. Even with that tool, though, you can get slight defects. You might have noticed these little streaks. We call that curtaining. Yeah, if we do it right, we got just spectacular quality of the surfaces. Limitation is areas polished. I think a couple of millimeters is all that's practical in maybe 6 hours, something like that. So on the other hand, you can go do something while it's polishing. So.
Thank you.
Sure.
Okay, well, that's our time. If anybody else has anything to add, that'll be great. Thank you so much, Dr. Nutt. This was an amazing presentation.
Thank you. It's happy to be able to present to people, and the questions, I think, were actually some very thoughtful and thought-provoking questions.